All right, let's look at 3 more word problems. Example 3, 4, and 5 in this video. A city has a population of 350,000 people. Suppose that each year population grows by 5.5%. I like this. Instead of A, can I use P for population? I'll say P of T equals P. How many people do we have today? Today we have 350,000 people. That's getting multiplied by 1 plus, what's the rate? Rate is 5.5%, right? And 5.5% in decimal is 0.055. So the growth factor is 1 plus 0.055. And I'm going to raise this to, well, the teeth power. But didn't they give us the t here? They asked this question. What will the population be after 15 years? Because it is 15 years, I will raise this growth factor to 15th power. So in fact, I didn't really find P of t. Instead, I actually found P of 15. So I'm going to go ahead and change this to P of 15. P of 15. And all I need to do is evaluate this. And since we are talking about the number of people, it makes perfect sense to round to the nearest whole number instead of saying a decimal of a person, right? So let me go to my calculator. Calculator over here. So let's type in what we set up, an exponential growth function. And you know exactly why I added it, because of the word grows by 5.5%. If it was going down, I would have subtracted that number. 350,000 times 1 plus 0.055, close the parenthesis, raise it to the 15th power for the 15 year. We got the number. It is so big. It is 781,360. Let me round that up because the decimal is 0.77. That's bigger than 0.50. So I'm going to round that up to 367 people. So that is how you can use exponential growth function to find the population in 15 years. Let me move this up because I have 2 more problems to show you, okay? So a couple of things that you should be careful about, to look for in these problems. Not only the numbers that you have to plug in, but like if it is growth, because of this grow, the word grows, let me use a different color. Because I say grows, that's why I added 0.005. If it was like decreasing, I would have subtracted it, okay? Because population is not always growing. Like for certain countries out there, population is actually decreasing. For example, South Korea. Anyways, example number 4. Suppose that a loan of 6,500 is given at an interest rate of 16% compounded each year. Assume that no payments are made on the loan. They said, find the amount owed at the end of 1 year. I mean, who would do this? Who would borrow a lump sum of money and not even pay back, not make any kind of payments? So I don't think this is a realistic problem because like if you borrow $6,500, wouldn't the bank somewhat require like, hey, you know what? I actually did this. I forgot about this loan I took. Some places do it. Some places do this. They don't require monthly payments. So you just pay the interest. I have one of that. Oh my goodness. All right. So let's find the amount owed at the end of 1 year. Because I'm doing 2 different problems, I think I'm gonna go ahead and write the function. I will say I'll just use A of t. A of t. The amount of money that I owe to this, I don't know, bank is going to be the initial amount, 6,500 times 1. Now, we borrow money. Do you think the debt is going up or going down? Going up definitely, right? Plus the rate of 16%. But 16% in decimal is 0.16. So you okay with me writing the growth factor is 1 plus 0.16, and t is just the number of years. So I wrote the function. The amount of money that I owe is 6,500 times 1.16 to the tth power. I can use this function to find out the amount I owe in any year by plugging in whatever the t is, whatever the time or the number of year is. A is asking, find the amount owed at the end of year 1, first year. So I'm just going to find A of 1. Plug in 1 into the function. 6,500 times 1.16 raised to the first power. So even though you only borrowed 6,500, how much do you owe after 1 year? Assuming that you didn't pay anything back yet. 6,500 times 1.16 times to the first power. Yeah, went up 7,540. My interest is not this high. I actually borrowed from my retirement plan, and that's why I don't have to make monthly payment back. But now I just remember about it. Oh, crap. All right, let's do the next one. Find the amount owed at the end of second year, year 2. I'm trying to move this up. None of my things are working today correctly. Whew, okay, hold on a second, you guys. I'll move it up. All right, so what I want to find for this part is I want to find A of 2, which is 6,500 times 1.16 raised to the second power. Well, that's going to go up even more, right? It's going to go up. So if I go down to my calculator, all I need to do is change that exponent to 2 this time. And that comes out to be $8,746.40. So you see how scary this is. You borrow somebody's money and you don't pay back. The interest is going to accumulate like crazy. Alrighty, so that was a very good example. Let's do the very last one. Example number 5. Now this is a special function, but you know, they gave us an equation, so all we need to do is just use it. So no worries. Let's read this. A species of animal is discovered on an island. Suppose that the population size P of t of the species can be modeled by this following function, where time t is measured in years. Now, if you think about it, it's a little island. Can you have infinite number of animals? Like, I know they're going to grow, right? They are going to reproduce and have, you know, baby of these animals. And the population is going to grow. But there is going to be a limit, don't you think? We cannot have infinitely many animals on this island because there's like limited resources and stuff. That's why we have this, because a little special function. I wish I get to talk a little more about this. If we have time after this, after test 2, we can come back and talk about the special types of exponential functions. So this is sort of funny. We have 600 on top of the fraction, and in the bottom we have 1 plus 3 times e raised to the negative 0.31 t. All right, so what are we doing with this? They said, find the population size of the species after 3 years. So, hey, I'll do that first. I'll do after 3 years first, which is simply plugging in 3 into the function. Okay, that is 600 divided by 1 plus 3 times e raised to the negative 0.31 times 3. So you just have to plug in 3. And we're talking about number of animals, whatever these are. So let's go ahead and round this to the nearest whole number instead of any decimal, okay? So give me 1 second. Let me extend my fraction bar a little bit longer. And I'm going to go and type this into my scientific calculator. So let's see. Over here, I'll type in 600 over 1 plus 3e raised to the negative 0.31 times 3. Okay, and the answer is 270. Hold on, why isn't this writing? Oh no, it's not writing. Hold on 1 second. Let me check my Apple Pencil. Maybe I need to charge it real quick. I'm gonna pause the recording real quick. So there will be 270. Let me round up to 5 animals. I think that's a good unit, isn't it? We're talking about number of animals. So, okay, so that's good. So in 3 years, we're going to have that many animals. Now, let's set up the next part. They want how many animals are we going to have in after 9 years. So let's set that up. It's exactly going to be the same, but we are plugging in 9 this time. So we're going to have more, right? 600 over 1 plus 3 times e raised to the negative 0.31 times 9. Okay, I'm now going to the Desmos Scientific Calculator, and I'm just going to change the 3 to 9 this time. Change the 3 to 9 this time. Am I going to have 500 and let's round that up to 7. I'm going to have 507 animals in 9 years. I'm wondering, how about if I wait 30 years? How about if I wait 30 years? How many animals am I going to have? 599.83 animals. How about if I wait 60 years? 599.9999995. What? How about if I wait like 100 years? Then I'm gonna have 600 animals. How about 1,000 years? 600. Guess what? Where did that number 600 come from? Isn't that the numerator there, right? So this is a special type of exponential function. If we have time, we'll come back and talk more about it. But for the homework this week, all you need to do is just use it. I want you to practice using this Euler number as the base on your calculator to evaluate them. So that is enough for this video. We looked at 3 application problems that you will see on your homework.